we welcome our next speaker, Rohan Giriraj, for Beyond the Basics, Advanced GIL Mitigation Patterns.
Uh, Good morning, ladies and gentlemen. I'm Rohan Giriraj, and the title of my talk is Beyond the Basics, Advanced GIL Mitigation Patterns, or GIL Mitigation Patterns. So let's jump right into it. So something about me, I am Rohan Giriraj. Again, I'm a software engineer at Autodesk, where I write Python scripts to streamline data ingestion and backend workflows. So I'm a little bit passionate about performance optimization, and I'm a huge fan of works like Roller Coaster Tycoon or Doom. So show of hands, does anyone here know about Roller Coaster Tycoon? Oh wow, okay, good. Doom, okay, a lot more. So, for those of you who don't know about Roller Coaster Tycoon, it is a very famous game that was developed in the 1990. It was in 1999, and it was a game that was purely written in x86 assembly. So, known for its insane performance, and it had the gameplay is still holding up till this day. And Doom, of course, it can run on anything. So yeah, it's a legendary game again. So yeah, this is where I began to learn more about performance optimization. Okay, moving on. So for today's agenda, we'll first get a quick refresher of what multithreading is. We'll have an overview of the GIL, Global Interpreter Lock, and we'll see a live demo of GIL's performance limitations. Then we'll explore multiprocessing and asyncio workarounds, and then we'll learn advanced mitigation with the Cython and the nogil directive. And then we'll have a small case study where we parallelize image processing algorithms using the advanced mitigation pattern that I just discussed about. Thank you. Yeah. Okay. The ultimate multitasker, Indian moms. So just to give a quick background, so imagine like all of our moms who were homemakers used to have insane time management and multitasking skills. So like in the case of my mom, when she's preparing lunch and in a South Indian household, you know that lunch usually means rice, sambar, some kind of dry curry, sabzi, and with papad and stuff. But everything that she prepares, she does so parallelly, right? So when the rice is cooking, she doesn't wait for the rice to finish cooking. Before that, while the rice is cooking, she starts to, prepare the sambar, and then she prepares the papadams and all those things. So she's a very good multitasker, and same thing can be said about processors, right? So when we look at a processor, we don't want the processor to stay in the idle state for too long. It should not be waiting. It should be using its time more efficiently. So that is perfect examples from what I could see is that my mom is a perfect multitasker, and I felt that this example sits really well with the way multi-threading works on processors. Okay, yeah, each of these tasks run in parallel. So she does laundry. She also helps me with. She used to help me with my homework and answering the door for deliveries and all those things. So all of these tasks run in parallel, but none is affecting the other, right? But just like in threads, there are also shared resources. So like the stove or the kitchen space, that is a shared resource. The house can be considered as one shared resource for that particular task. So let's understand the GIL. So the GIL, or the Global Interpreter Lock in this case, is a mutex or a mutex, which basically is a type of lock that protects access to certain Python objects. So it basically doesn't allow a particular thread to access another Python object when another thread is using it, right? Only one thread can execute Python bytecode at a time, and it prevents native threads from in a single process and acts like a talking stick, which means that any person, so talking stick basically means that if you have a stick, only then you can talk. If you don't have a stick, you don't talk, right? So that is the basic understanding here. So it acts like a talking stick between threads, where if the stick is passed to a particular thread, it can execute, otherwise it doesn't execute, right? So why does the GIL exist? So first things first, it simplifies Python's memory management. So single-threaded execution is Python's forte. So it simplifies the memory management for it. It eases the integration with C extensions. And we all know, for people who have coded in C, we know that memory is a is a bane of C. So it eases out integrations with C, and other in Python implementations. There are like Cython, IronPython, which basically have Java or .NET backends. They don't really have GIL. The only one that has GIL is CPython, which is the one that is commonly used everywhere. And this GIF that I have here is basically like an accurate representation of how multi-threading works in the context of Python. You can see that none of those boxes overlap each other, which means that at any given point, only one single thread is being executed. So that is the idea behind the GIL. So when does GIL hurt performance, right? So GIL is great for IO-bound tasks. Python threads also work great for IO-bound tasks. The GIL is released during wait, and then other threads can take over and start to run. And this issue, however, severely impacts CPU-bound tasks because at any given point, only one single thread is being executed. There are no threads. They offer concurrency, but not true parallelism, right? I feel like there was one question from somewhere here in the previous talk as well about how asyncio is not truly parallel. And yeah, you are right. It is not truly parallel, but for IO-bound tasks, it's really good. But for CPU-bound tasks, it's a little difficult. Okay. So let's talk about what are the existing workarounds that are there for GIL currently. So one is, of course, multiprocessing, and the other one is asyncio, right? So multiprocessing, yeah, it spawns new processes. Each new process gets its own Python interpreter, memory space, therefore its own GIL. This allows for true parallelism, and it's best for CPU-bound tasks that can easily be split into independent chunks. The downside, however, is that high memory usage and slower communication between processes because Python does what is called serialization between these multiple processes to keep track of state, and it's called pickling, right? And pickling and unpickling of data requires higher overhead than with a standard threaded approach. So that is one of the disadvantages of multiprocessing. Asyncio is a single-threaded thing. Again, it uses cooperative multitasking, and it uses an event loop to manage the switch between the different tasks. So when we come to cooperative multitasking, it basically means that certain tasks have to act benevolent, where they yield the control to other threads while execution, so that it doesn't really affect the way that the programs are executing. It's best for structured code for IO-bound tasks like web servers. I think Alan previously showed how he was using a fast API web server, which is basically an IO-bound task because when you send a request, you're waiting for a response and then you continue. So that is kind of like an IO-bound task where you are doing like a standard wait receive pattern. And then the downside, again, this is not for CPU-bound tasks. A single thread will still be blocked by computation. If it is continuing to compute, it is going to stay in a stuck state. Okay, now the GIL bottleneck. So we'll just do a simple demo to see what a CPU-bound task can do while counting down. Like how does a GIL prevent the CPU from running when you're doing this? So we'll run a simple task which is counting down from a very large number. So we'll run this 2 times. One will run sequentially and the other will run with 2 threads. So the hypothesis is that threading means fast, right? So this is going to prove that assumption wrong. So, okay, let's see. Is the terminal visible for everyone? Like, zoom in a little bit. Okay. Let's just see. Okay, and this. Yeah, this is the file. Okay. I'll get to the code in the meantime, right? This is not visible? Oh no, okay. Yeah, I can zoom in 1 second. Yeah, let me just see the themes. Is this good? Okay, great. I think I've zoomed in a little too much. Hold on. Yeah. Okay, so This is the simple script that I was talking about to demo the GIL and its limitations. So we have a count, which is 100 million. And within the count, we have a countdown function, which is a simple loop, while loop that is, counting down to 0. And then we have a start time and end time, and we are first calling the sequential execution, where we are calling this function twice sequentially. And then we say that, hey, the sequential execution took so many seconds. And then we have the threaded execution, where we have two threads which are calling the same function. And then we have a start time and end time, and we're calling the start thread to start the process, and then we are calling the second thread as well, and then we are joining it, and then we are saying that the threaded execution took so many seconds. So this is basically a very straightforward CPU intensive task that even you can do on your laptop to see how GIL it has certain limitations. So here you see sequential execution took 7.2 seconds, while threaded execution took 8 seconds. So clearly you can see that it's taking more time than expected with the threaded execution. So this is what I meant when I was talking about GIL's bottleneck. Okay, then let's come to the main crux of this talk, which is basically advanced mitigation strategies. So when multiprocessing is too heavy, like I said, it has overhead, right? You have a small memory overhead when you're unpickling data, and then you're running it again. So you need to have some amount of some workarounds to this, and you need to step out of pure Python. So you have two options. One is writing C++ Rust extensions, which is like a custom library that you're running and then calling it from within Python. So this code can run outside the GIL's control. Most machine learning libraries, numerical Python libraries like NumPy, SciPy, these are all written purely in C, and they run outside of Python, which is why you see that it doesn't get stuck with the GIL and is pretty parallel. I think even PyTorch, please correct me if I'm wrong, is actually originally written in C++. If anyone, yeah, okay. So that is basically one of the things that you can do. So the pros are, again, maximum performance, and most machine learning algorithms today are being trained based on these extensions. And the cons are it's complex, it requires knowledge of another language and Python's C API, because you're basically writing Python bindings on top of that code. So it requires you to go and fix each and every issue that occurs, not just with the code that you're initially writing in that different language, but also with the bindings. Second option is the one that I'm going to present with you today, is using Cython. It's a superset of Python that compiles to C, and this will be the focus for today. So the pros are, it lets you write Python-like code, and it gets compiled to fast C code. It also has a special directive called the nogil directive to release the GIL. And the cons are, it requires a compilation step and some new syntax. Even though syntax is pretty similar to Python, it still requires a knowledge of certain functions or certain directives in order to compile properly. So, quick introduction to Cython. Cython is basically Python with superpowers. It is both a language and a superset of Python and a compiler. It translates Python-like code into highly optimized C code. And the magic in this case is the GIL, which is the most powerful feature for parallelism. And by wrapping a particular section of code with that GIL directive, it will basically run outside the nogil directive. It will run the code outside of the GIL. So basically, you don't have to worry too much about writing separate extensions or changing the runtime. Nothing. Just make sure that that nogil directive is included. So how Cython works, a quick demo. So 3 main steps. First, you write your code in a .pyx extension with this .pyx extension, right? And then you add C-type declarations. So one of the main reasons why Python is slow is because it's dynamically typed. In this case, you're also ensuring that your Python doesn't have to assume the types of certain data that you're inserting. So you have to specify the type declaration using C. And then you have to create a setup.py file, which basically it's like a make file in this case, but it's like a setup.py file, which will tell your Python script how to compile your pyx file. And then you have to, of course, run the setup.py file and then build it, right? So in this case, that build_ext is like basically an parameter that you pass, which tells it that you have to build external modules, and that in place flag that you're seeing ensures that whatever is built stays within the same directory. You can also set custom paths to different directories if you want. So when you do this, you basically get an extension module with the extension .so or .pyd. So SO is usually what you see in Linux when you're using GCC, but PYD is something that you can see in Windows when you're using the Visual Studio compiler to basically compile stuff. Okay, now we'll come to what we are trying to do here. We are going to use Cython and OpenMP. Now, anyone familiar with OpenMP here? Okay, great. One or two people. Okay, so I'll just give a quick introduction. OpenMP is nothing more than a library that is written in C, C++. It's called Open Multiprocessing. It basically is the library that is used in most game engines today to run, shaders and all those other physics engines to basically, run everything end to end, basically. So it actually was written initially in Fortran, not even C, C++. It was written in Fortran, and then it got ported over to C and C++. So it's pretty old, and it's like battle tested, basically. And Cython, we are lucky is that it has support for OpenMP built in. We don't have to do anything else. We just have to call it, and it'll allow us to parallelize 4 loops. So that's great. And in this thing, the demo that we are going to see shortly, it has 2 things, a nogil context and a p-range function for parallel loop execution. So before we go into the demo for the case study, we'll do one thing. I'll show you guys how, Cython code looks like. Okay, I think, no, not this one. Yeah, so this is the Cython demo. It's a pyx file, as you can see. So a very simple, pyx file where you are just taking a def. So this looks exactly like a Python code. So you have a function. It's called sum of squares. You're passing a number, but here you see that you are actually defining the types. You're doing cdef long total, which is basically the long type that you see in C++, C or C++, and then you're having a total. Then you have the int, so you're basically looping through the list, and then you're adding that total to basically like the long that declaration that we did. So it's sum of squares. So for each number, you're doing a sum of squares. So let's try to execute this. Okay. Right. Okay. Right. So if you remember, I was talking about building the file, right? So let's take a look at the setup demo file as well. So this is the build file for this particular script. So this is the script. This is what the build file looks like. So if you see, we are using setup tools to build it. Then we have Cython, which is the package that we are using. We are importing it. And luckily for us, they have built a very convenient function called Cythonize. So basically what you do is you have the setup, and ext modules here means external modules. And then you are calling the Cythonize function over the script that you just created, which is Cython demo_demo.pyx. So let's try to run the setup file first. Setup.py build. It's building the external modules, and we do it in place, so all of the compilation results stay in the same folder. Okay, so I think it's already built once. So you can see here, this is the run that we created. So it's an SO file. It is basically a binding. So we can take a look at that as well. Cython demo, I think this is the one, yeah. Okay, this is a binary file, so you can't open it. I thought we could. But again, it also compiles to a C code. So if you see this is the C code that is generated from the pyx file that we wrote, and it makes no sense to us because it's got nearly 8,000 lines, if I'm not wrong. Yeah, 7,000 something, 600 something. Yeah, 7,664 lines of absolutely code that makes no sense. But this is so efficient that it runs, the computer understands it. And that's what we should concern ourselves with. So we know that the build has completed. Now, how do we call it, right? So I can just go here and this is the, hold on. Just clear my terminal first. Right, so we can just do import Cython demo, and it is imported because the build file was already there. And now we can just call Cython demo dot sum of squares, and in this I can give a very large number. Hopefully it works. Okay. Okay. Yeah, so there you go. So this is how the demo works. This is how Cython works. So you are directly calling the, the file that is compiled into your Python script and then executing it. Okay, great. Now let's go to our case study, which is high performance image processing. So the task here is to convert a very high resolution image that we have. Slide showing. Yeah, high resolution color image to grayscale, right? Simple task. I believe anybody who has dealt with computer vision or even done a little basic pillow editing image, you know that you can convert anything into grayscale. It's very simple. It's just a simple function call. But this task, it's CPU bound, so there's no IO involved in this. It can be massively parallelized because no two pixels are dependent on each other. They are individual. They don't have any relation to each other. And it's a very common task that spans across domains. So you can see it in web development, you can see it in image processing, you can see it in so many other applications as well. So we have two files that we'll be creating. One is the pure Python version. So in Python version, what we'll be doing is the logic is pretty simple. We will be taking the image, we'll be putting it inside a NumPy array. So it'll create a three-dimensional NumPy array where you have RGB values, and it'll be the one, and you'll have this formula which is basically the luminance formula. You apply this on each pixel, and then you can convert the image to grayscale. Right, and we'll be doing it using loops. So height and width for each this thing will be like a matrix. So we'll be going through each loop and converting the pixel value one by one, right? Then we have the Cython nogil version. And in this, what we'll be basically doing is we'll do the same thing, but with the help of Cython along with OpenMP. And here, there will be some changes from the previous approach, which I think we'll go over when we are going through the code. First is that we will be using typed memory views. We'll be using unsigned characters, which is unsigned chars, for direct C-level access to the data. And the nested loop will be wrapped within the nogil directive. And the outer loop will be, which is the y and x, which is going to be the height and width, will be inside the using the prange function for OpenMP, so that it can run in parallel. Okay, I think I can go to the code. Okay, so this is the first one. It is. Yeah, so this is the code, right? So first we have a very simple Python code, def python underscore grayscale, which basically is the pure Python implementation. Doesn't even use GIL, by the way. So what we are doing is we have the image, we are opening the image, right? We have the file not found error, of course, like try catch block. Okay, that's all boring stuff. Then we have the image data. And within the image data, we are basically taking the image and putting it inside a NumPy array, right? So it converts it into a three-dimensional NumPy array with red, green, blue, right, RGB. And then what we're doing is we're taking the shape, which is the height and the width of the image. And what we're doing is we first create a separate NumPy array called with the same height and width, where we'll be writing our grayscale image to. And then we will be running this loop, and the loop, of course, is being timed. And within the loop, you have the RGB. You are basically looping through height and width. And for each RGB, you are applying this gray value formula, which I just showed you. And then the data is being written to the other NumPy array, right? So that is the pure Python approach. Then we have the GIL grayscale approach. So in this case, instead of just running a simple loop, we are actually calling threads. So we have row per threads, and then we are dividing it by the basis of the number of threads. So in that, like, each thread will be dealing with certain number of rows within the image. And then we're running the same loop, and then we are appending it and then we are starting it. So all that stuff. So in the meantime, while I'm explaining the code, I'll just run the code so that, it finishes on time. Yeah. Okay, so now that this is happening, we have the threads, and the threads are joined, and then we are seeing how much time it took for the thread to complete execution. And then, of course, we return the image. Then I think, yeah, that is it, I guess. Yeah, for pure Python approach. Now let's take a look at the Cython approach. Now within the Cython, this is where things get interesting, right? You're importing NumPy, but then we are also importing the C bindings for NumPy. So it's C import NumPy, and then from Python, CPython, we are importing prange.parallel. So remember, like OpenMP has inbuilt bindings within Cython, so you don't have to necessarily specify it. So prange is from OpenMP, and then we are calling that. And then again, we are calling the C level bindings for Cython as well. So now we are also adding these two, decorators here, which is basically bounce check and a wraparound. To be very honest with you, I don't know what it does, but yeah, when I Googled it, they said that I need to add this, otherwise it was, it was returning a seg fault error. So I'll have to check why this is the case. But then we have the grayscale Cython function, similar to what we saw with the grayscale Python function. But instead of passing the image directly with like a NumPy array or something, we're using unsigned characters here. And this is the source image. This is the destination image. So we are taking two arguments here. Then again, we are defining the height, width, and we are also defining the x and y, which in this case will be for the source and destination image. No, sorry, the loop variables basically. Then again with nogil. So this nogil is the place where we release the GIL. So this is the nogil directive. And within this, we are running the parallel loops. So y and p range, height, and we are saying it's a static schedule. Again, I'm not sure why that is required, but then we have the x in range. So why every height loop is running in parallel, and within that we are converting the value for each particular column, basically. And then, of course, we have the conversion of the destination image. We have the source image coming in, and then for each one of the values, red, green, blue, which is RGB, we are running the luminosity score and converting it into grayscale. Okay, I hope that was clear. Now, let's take a look. So, oh yeah, one more thing. So and this is the driver script that I'm using to run all of these. So this basically calls all of the image Python, image Cython, and then it runs a timing script over each one of them to see how it is being executed. And the image that we are using is the image of Curiosity rover on Mars, right? So this is a very high quality image that I got from NASA's website. So I felt that it was good enough for this test. So let's see the execution, and it seems like the Curiosity portrait took 131 seconds with just pure Python, and now it is running with 4 threads. So it's going to take even more time using the threaded approach, and then we'll see how much it takes with the Cython approach. So while this is happening, any questions? Does anyone have? Yes. Mm-hmm. Mm-hmm.
If there any error comes, right? So how do you debug it? Like it will be like C what we get the error, or it's a pure Python what we get the error?
Yeah, I'll come to that. So that is one of the caveats of using this. I'll come to that in a second. Any other doubts? Yes. When to use async?
Async IO or multi-threading?
Okay. Okay, it depends basically. So I mean that is the standard answer for everything. It depends, but multi-threading. So async IO can be used for scenarios where you don't want certain like when we use async IO, especially in our case. Okay, looks like it finished executing. Okay, so I'll just answer your question first. So in the scenarios that I use async IO, I know that it is a single-threaded this thing. I know that it is single-threaded, and you don't have to deal with multiple threads because threading again is a resource-intensive process, right? So for each process, if I'm spinning up multiple threads, it is going to cause some bottleneck or the other. But in the case of asyncio, we know that it's a single thread and it is using cooperative multitasking. So when you say you're saying async def something, you know that that function will basically yield its control to another function, but it is running on a one single thread. No, but async IO is not good for certain scenarios where you're having like a large number of where you're having a large number of IO operations happening. Async IO is good where you know that you're limited by your processing, and then you just need one single thread to manage one particular aspect of an application, right? Okay, so yeah, coming to the results. So you can see that the threaded version took 131.4 seconds, and then the Cython version took 0.03 seconds. So you can see the performance comparison between all three, and you can see that Cython was 4,338 times faster than our standard approaches. So yeah, let's come to the conclusion. Yeah, we're done. Okay. Yeah. So just to conclude, right? So the GIL simplifies C Python's internals, and it prevents true multi-threading on CPU-bound tasks. And then standard libraries and async IO are the first things that you should use, right? And you should first see if this really fits into your workflow before adopting it, because like that person said that it is difficult to debug code when it is in two different stack traces. One will be in the C and the other one will be in Python. So you have to be very careful about where you use it and how you use it, right? And for maximum performance, this is a very good tool, but again, it comes with its own set of caveats. And the nogil directive, which releases the GIL, and the p-range function is the key to unlocking maximum parallelism, which allows you to sidestep the GIL. There were some more slides, but yeah, I think we're done with the time. Thank you. If you have any questions, please reach out to me.
Please join me in giving him a round of applause. Thank you, Rohan. That was a wonderful session.
Yeah.
Yeah, please connect with him in the offstage.